I think we can start. It's 01 at my location. DJ, your stage.
Sure. Can everyone hear me? Or can someone hear me?
Yep, everyone.
Okay, perfect. I'll go ahead and get started then. Okay, so welcome to build team training on Helm charts. We're going to go over what the Helm charts are. We're going to do a brief refresher on the Kubernetes objects that the Helm charts create, and Kubernetes in general, or the Kubernetes objects in general, and then do kind of a deeper dive into creating Helm charts and our Helm charts that we have currently at GitLab. So it's meant to be fairly technical, but hopefully anyone who isn't already familiar with the Kubernetes stuff will still get a little bit better understanding of what it is we're packaging up here. So the first thing is, what is Helm? So Helm is a tool for managing Kubernetes packages, which they call charts. So Helm, the program allows you to create new charts from scratch, kind of like a generative skeleton template that you can fill in. It can package those charts into chart archive files, which are TGZ format. The tool can interact with chart repositories where the charts are stored, to download them and install them. And it's used to manage the release cycle of charts that have already been installed with Helm into your Kubernetes cluster. And I just provided a link to kind of where this bullet list came from. So that's the purpose of Helm itself. And then what is the chart? So the chart is an archive, a targz archive that contains basically a folder structure that has its other dependent charts as archive files within it. It contains the Kubernetes templates that you would have normally been passing to the Kube API that you would use to deploy your application to Kubernetes. It also has some Golang template helpers to help populate and fill in those templates, those Kubernetes templates. It contains some default configuration that can be overridden by the user, and also some post-install, pre-install documentation that while you're installing the chart will be printed out to the screen to give users additional information on what they've just installed. So that's what Helm and the Helm charts are as a description, and we'll get deeper into what the commands look like and what the charts themselves actually look like a little bit later in the architecture. But just for as a refresher for people who just to understand what Kubernetes template files I'm talking about when I mention the template files that are contained within the Helm chart, and also for people to get an idea of maybe who aren't familiar with Kubernetes of what sort of objects we're talking about that they can go and research later to find out more about. So I'm just going to run through these fairly quickly. So if you have any questions about these, I'd recommend revisiting this presentation and or asking questions at the end, but revisiting this presentation and doing some research on some of this stuff, because this is the Kubernetes side and this talk is more about the Helm side that packages it up. But I did want to run through it real quick. So as a refresher, Kubernetes has a bunch of these objects that make up its your application in the cluster. So at the basic lowest level, not the lowest level, but the lowest level that we're concerned with as application developers is the container. And these containers are defined using similar syntax of Docker containers, in a syntax very similar to what you would see with Docker Compose. Interestingly enough, in Kubernetes, we tend to not actually directly create the syntax for the containers or directly create the containers, but instead we kind of give enough information to the scheduler to tell it how to generate them. And a container in YAML format in Kubernetes is kind of defined like this. It has a kind container, has name, the Docker image that it pulls from, and potentially override for the command that it runs, environment variables, information on its CPU resources that it requires in your cluster, and the volume amounts that it needs to access its data. So this is actually very similar to the flags that you might pass Docker itself, or the type of file that you would pass to Docker Compose. So in that regard, this part of it is similar, but we don't actually normally send these directly to Kubernetes as a definition of a container. We use the objects that wrap this to do that. So wrapped around a container in Kubernetes is the idea of a pod. So a pod in Kubernetes is a collection of containers that function as one single unit. What that means is that they all the containers within a pod have the same volume resources. So they have the same volumes, this access to the same volumes. They have the same deployment properties. So that means all the metadata around how to deploy them and how to redeploy them and roll them back and all that other stuff is the same among all of them. And also importantly, they have the same network. So they all look to each other like they're on localhost to each other. So they can only differentiate by port, essentially. You often see, well, you can create multiple of these containers in a pod specifically for this, but also things like helper containers and sidecar containers and stuff like that will kind of end up in the pod like this. But in Kubernetes, we tend to not directly create pods either. We instead also tell the Kubernetes scheduler, we pass it some template on how to create pods. But a pod looks like this. So it actually basically under the first two lines, it's basically a bunch of just that container specification. This is actually just an array of containers, a kind of pod. And we had the volume amounts from before, and the thing that's been added is also the definition of those volumes now. Because like I said, all the different containers share the same access to the same volumes. So the definition of the volumes is set at that level. So that's basic definition of a pod. This doesn't really have a similar spec in Docker Compose or anything like that. Then we have something called a replica set. So the replica set is the thing that contains the template that tells the scheduler how to create a pod. Like I said, we don't directly create containers. We don't directly create pods. The scheduler creates the pod from this template contained in the replica set. It includes the number of pods to create, hence the replica name. So it defines how many of the pods should exist. It defines the conditions on when and how to create them. So are you allowed to create one extra while you're taking one down, or can you only at maximum have this many? How do you do a rolling deployment, stuff like that? And interestingly enough, we often don't, while you could create these directly in Kubernetes, we often don't create these directly either, even though they do contain the template for the pod. We'll eventually get to what we do create, I promise. But the replica set looks the same, and you'll notice it basically, I've cut up some things, but it basically just wraps the pod spec that we saw before. So we have a kind replica set. We now have the number of replicas. I've excluded off any conditions or anything here, but then we have the definition of the template with some metadata, but within that template, we basically have our pod spec where you see that containers array that then lists the containers. So this replica set is just the template for the pods plus the number of replicas. So then finally up to the kind of level that we actually create is the deployment object. It contains the template for our replica set and pod. So it once again just wraps that previous config. This is what we actually tend to create as application developers for Kubernetes. We create a deployment. The deployment gives you the ability to manage a revision history. So it kind of gives you versioned replica sets and with names and additional metadata so that you can create a new deployment, roll back a previous deployment, and track your deployments while still seeing what the status of your old replica set is, type thing. So it kind of wraps it together to make it nicer for deploying to Kubernetes. So that looks like this is basically just wrapping the replica set. So you see we have a kind, API kind of deployment, some metadata, a spec, which is basically our template for our replica set. And then under that is our replica set, which contains its templates and our pod and everything like that. So that kind of, the deployment is the main object that we create in Kubernetes to define our application. In addition, we also create other objects directly, unlike the replica set and pods. We have things like services, which define how you expose pods to each other with internal DNS and networking. They can also be bound to an external IP to be exposed externally. But by default, they just provide internal networking between the pods and between namespaces if you set them up that way within your cluster. We have config maps, which are just a plain text storage meant for configuration, but they can be used for any type of plain text storage within the cluster. And then we have things like ingresses, which point to those services above, but they're specifically designed to route external traffic to services. And you often see these ingresses run against a load balancer in the cluster. And then we have other things like namespaces, volumes, persistent volume claims, and secrets as objects that we tend to directly create in the cluster. So kind of like that being the overview, kind of getting back to Helm and kind of where these interlink. So kubectl is the command line client for communicating with Kubernetes. That's normally how you would deploy to Kubernetes. So normally you would create your deployments, those config files, you would create your service files, you would do that on your local machine, you apply them to your cluster using the kubectl command, as you see here, kubectl create. Once you've already authenticated with your cluster and set up which namespace you're looking at, you do kubectl create and you pass it the different files that you want that define what you want to create. You would then, to continue using those files and editing them and updating them, you'd use things like kubectl apply, or you'd use kubectl edit to kind of get an internal editor to manage those objects and iterate on your deployments and have the cluster redeploy your changes and stuff like that. So that's normally what you would do with kubectl. When you're using Helm charts, instead of iterating on the deployments like I was just mentioning before, instead of updating those deployments directly, you instead tend to, as a user who's using these templates, you tend to iterate instead on the configuration. So think of it kind of like in Omnibus or GitLab RB file. Then instead of you, the user, iterating on the cookbook files and the recipe files and stuff like that, what you're actually iterating on is just that config file to adjust things and change your deployment. And then those edits use Helm to trigger new deployment. So the chart author, so us in this case, defines what those deployment templates are and what the different options are. And the chart user, the person installing the chart, modifies the configuration, and that's it. Helm basically ends up running those kubectl commands for you. It doesn't actually run kubectl, it uses a lower level API, but it essentially sends those templates across. It runs those commands for you using the chart author's R deployment and combining that with the chart user's configuration. So jumping full back into Helm, we're going to take a look at the architecture. So it's made up of something called a tiller server. So this is what gets installed into your Kubernetes cluster. It's a deployment that actually installs in your cluster. While it's sitting there, it can be passed a chart, it can be passed the config from the user, and it combines them to create a release. So what it does is it's that application running your cluster is actually in charge of rendering the templates that get passed it and then it communicates with the Kubernetes API to apply that release to the cluster, to apply those new deployments to the cluster. And it doesn't have its own database. It instead tracks all the information about the releases and the things you've installed using Helm, using the config map objects in the cluster, the config map being that text-based storage that I was mentioning before. The other piece of the puzzle, so that's one of the pieces, was the server, the tiller server that sits in the cluster. The other one is the Helm client, which is the user command line client for Helm. So this command line tool is used for communicating with the server. It passes the configuration for your charts from your local machine to the server. It can also be used for local chart development, so you don't need to always be communicating with the server. It does the things like I mentioned before, generating the skeleton framework for a chart and stuff like that. And it uses your existing kubectl config, so your auth login on kubectl to communicate with the cluster. And it's also used to install tiller to the Kubernetes cluster. So once you have your kubectl config set up for your cluster and you have Helm installed, running Helm and it actually just goes out and deploys the tiller server into your Kubernetes cluster. So now we're going to jump into the charts and building them, starting with just what the file structure of the Helm charts look like. So charts are just a folder, or defined in a folder while you're creating them before you package them up. They're defined in a folder where the folder name matches the chart name. So in this example, we're using GitLab runner. And this is, for this first example, this is essentially the GitLab runner chart. Well, this isn't actually the chart, but this is, oh yeah, this is the chart. Yeah, this is the GitLab runner chart that we actually have in our repository that I'll be using as an example here. So within this folder, we have a chart.yaml, which is metadata information with the chart, a license file, which of course is the license for the chart, README, which is a README in the source code. So when you're looking at the chart in GitLab, this is gives documentation information in the chart on how to configure it. The values.yaml, this is the default configuration values for this chart. This is where the values that the user can override are defined, and often a lot of documentation goes into that file as well. There's a requirements YAML file, which contains information on the chart dependencies. Runner doesn't have dependencies on other charts, but for example, GitLab has dependencies on Postgres and Redis, and those things have charts. And so the requirements .yaml might contain those in specific versions of the charts that they depend on. There's a charts folder within this folder, which is where those required charts end up sitting. So there's just archive files for, not in Runner's case, but in GitLab's case, it'd be for Postgres and Redis. Their charts would be sitting in that charts folder. There's a templates directory, which contains the different Kubernetes templates with Go. So Kubernetes templates that we were talking about before, but within them, they have Mustache templates as well that Go will process before installing into the chart. And that's where we're able to combine the config that is exists in values.yaml and the user's values to generate the different charts. And there's also notes.txt by default in the templates folder, which is a plain text file containing short usage notes. So this gets printed out after a user installs the chart. So it's the basic file structure. I'm just going to jump through each one and kind of show you what it looks like for GitLab Runner from most of them. So the chart.yaml looks like this. Defines the name, assembler version, description, keyword, where to look for the source and documentation, and list of maintainers. The requirements YAML. In this case, like I said, Runner doesn't have a requirements YAML, so this is actually the one from GitLab. So it just names the dependencies. It gives the version of the chart that we require, the chart repository where it will go look for the chart. This is actually a build time step though. So during build time, it will bring down that version of the repository, and then it will include it in the archive of this chart when we package it. And then there's a condition on whether to even include this dependency. So in the GitLab chart, for example, in your values file, you have the option of saying whether the included Redis is enabled or the included Postgres is enabled. So that's the condition here, that these dependencies only get used in the case that that Redis and Postgres are enabled. We have our values.yaml. This is back to the runner. This is just the one that we defined. In general, you define the image. In this case, we have defined it as our GitLab runner Alpine image. There's a couple mandatory settings that aren't set by default. So the GitLab URL is mandatory, but it's commented out by default because we don't know what it will be. And the runner registration token is also required, but it's commented out by default. Then there's values that impact how the runner is set up. So how many concurrent runners you can have, the check interval for the runner. And then there's information on the runners themselves. So in Kubernetes, the runner, for example, gets started as kind of like a runner manager, and it's in charge of starting up other runners in the Kubernetes cluster. So this runners subobject defines the default image for those, whether they're privileged or not. And then in GitLab CI, we have this idea of a separation between what images get started up. So whether they're the actual build images or whether they're the service containers, or whether they're helper containers. And those all have resource limits on how much CPU they can use and stuff like that. But this is just an example of a values file. So a user, so this is the default one, and then a user will be providing their own that overrides some of these defaults, so the values get combined. So we also have a bunch of templates. So this is, I'm assuming this is going to be our runner template. So it's actually just that deployment Kubernetes object we were talking about before, but you'll notice there's these mustache curly braces throughout, where it will actually be processed by the tiller server and given the value information that the user has provided combined with our defaults. It has a couple things. It has some helper functions as well in the mustache templates that it's using here. It's processing these using Go. So there's this idea of a template. So that's a function that will run the helper function called full name. The call out to .chart name and .release name below, those are just directly outputting information from the metadata, or you'll see here in a second the values file. So I'll just, through the next couple of slides, I kind of go through the rest of this deployment because it's kind of long. So we're down into this is still the deployment, just lower down. We're defining different metadata, but everywhere you see these curly brackets is where information is being pulled in from either helper templates or from the values file. So you see images set to values.image. We have a couple other functions, helper functions you see here called like default, and we have action pipes in these Go templates that we can pipe to quote and stuff like that. And this is kind of the rest of the file where we see the rest of setting up the pod in the container. So it's basically the Kubernetes templates we saw before, but you see a bunch of the, instead of hard coding that information into the template, we have a bunch of this that gets generated from the config and from these helpers. So another file we have in in the runner is this secrets.yaml. So we talked, I mentioned that secret was another object that you could pass to Kubernetes. It's basically a config, well, it's basically a config map, but it has a couple things going for it. It's expected to be base 64 encoded, which of course everyone knows, so it's not that that secret. But in addition, the Kubernetes is given, it knows because it's a secret that it should be more restricted on where to show this and expose it. In things like the UI and on the command line, there's basically always flags to get it to show at this point in Kubernetes, but often it won't show up by default unless you take some additional action to see what's actually inside it. And then it's still base 64 encoded, so you'd have to unencode it. Often when you're creating secrets using kubectl, it will do the base 64 encoding for you. When you're creating the object directly here, you'll notice lower at the bottom, we actually pipe it to a B64 encode. When you're creating the object directly, it doesn't by default base 64 encode the data. It's expecting you to do so. So it's more a feature of the kubectl command that often does it for you. So we're just kind of replicating that here. So we've put the runner registration token in a secret. There's also these template helpers. So we were looking, when we were in the deployment file, we saw this reference out to template full name. This is where it's defined. You can see the bottom template definition full name. And that's kind of the syntax for this. In the case of these Go defined templates, they always have to output something. Essentially, their purpose is to output like print out strings. So that's what you see here. In the case of the runner, this is really all we have. We just have the defaults. In the case of GitLab, we have some fancier stuff, which I think I will have in the next couple slides. Yeah, so this was just a very basic one that we used in the runner. Here's an intermediate one that we use in GitLab. So in addition to those other ones, we have this one where it kind of, in GitLab, we have our GitLab chart essentially allows you to install the EE version or the CE version, and we use a value flag called edition to determine that. So you can set what the EE image is and what the CE image is from the values file. We have it defaulted, but which one gets used during install is based on this .values edition variable. So this is a template that conditionally either uses the CE image or the EE image, and basically when we're in our deployment, when we're adding in which image we want Kubernetes to use, it'll be making a call out to template gitlab.image to render the correct Docker repo. And then this is kind of the more advanced, oh yeah, this isn't, so this was intermediate. This kind of shows how you can use those templates. So this is a config map object from GitLab again, our GitLab chart. So lower down in around the middle of this this object, you see that we have the normal way of calling our templates like template gitlab.fullname and stuff like that. But at the bottom, you see this call to this variable we've set called post reconfigure script that we are piping to the indent for, so that it indents all the contents of that custom code for from the left to be valid syntax for this Kubernetes object. The reason, if you look back at the top, that we essentially called into this template using an include instead of just calling lower down template is the template function in here doesn't allow us to pipe to indent. So this is like a workaround. So when you have a template that you want to pipe its output to other actions, you have to first use include to get it into variable or just wrap it in. You have to use include to wrap it in brackets or something instead of using template and then pipe it. So that's just a bit of side information on how to use the templates and some workarounds for limitations. And then here is an advanced usage of template. This is one that we haven't actually committed yet to the GitLab chart, but was one I was working on. It's kind of interesting. So I changed. This is its own file. It's in a storage.template file. Just to jump back to the .template files. Basically, all the files in the templates folder will have the template renderer run over them. So if they have these mustache curly braces in, they'll get rendered out. But if they start with an underscore, they're considered private, so they get processed. But at the end, at the end they aren't included as files that are trying to be installed into your Kubernetes cluster. So that's why this one gets processed and it defines stuff in Go, but it doesn't actually, which is then used in the rest of the rendering, but it doesn't actually get, it doesn't attempt to add this as a file to your cluster or something like that. Because it couldn't, because it's not a Kubernetes object. But in this advanced example, I've created a new one. It's private. It's storage.template. In this case, we're kind of taking advantage of the Go language to do some stuff that that Helm has limited us. So one of the limitations of Helm is that we ran into is that within your values file, you can't use conditions within the values file itself. You can't use previous values within the file that determine other values. So one example of that in the GitLab chart is that we have all these different persistent storage layers. We have persistent storage for GitLab itself with the registry and the data and the config and separate volumes, but there's also persistence for Postgres data and Redis data, and those are even in different charts. By default in values, if you want to do something like change the storage class, what the storage class does is allow us to use different types of, tell the cluster use different types of drives or something like that. So in the case of us wanting to use like SSD drives, the user would actually normally have to go into the values file and set the storage class for every single different, well, we could have either only allowed one setting that we applied to all of them, but that wouldn't have actually worked because we're using separate Postgres and Redis charts. So in order to adjust the value of those charts without forcing the user to set multiple values, this essentially added an extra variable called use storage class as a global, and then it takes advantage of the fact that these Go templates are processed kind of at the beginning of a rendering run to use this set function to go in and kind of reset the values after the fact. So regardless of what value, for example, GitLab persistent, GitLab etc was set to, this global use storage class will override it, and same for the ones below. So this is not this is listed as an advanced one because this is actually not an endorsed usage of Helm. It's more of a workaround for some limitations that we're attempting to do to make it nicer for the user so they don't have to set so many things. And it's possible that this sort of usage would break. At the moment, it doesn't actually fully work with subcharts because there was a bug in Helm where they didn't sort the templates before running them. So any run, it could be that the templates that actually use this data was being processed before this template was run. That's actually fixed and will be released in the next version of Helm, but that's one of the reasons why this currently isn't part of our chart. But this is something that is possible and will work with the next release of Helm, but it's still not an official documented or endorsed way, but it is a way that we can use to, well, it doesn't look that pretty for us, it does give us a way to make the configuration easier for users. So when we don't have another option, we need to make it easier for users. This sort of craziness is one of the things we can look into. So the kind of helper templates that already exist by default, these are the different, you saw things like indent and quote and base64 encode and stuff like that. Those sorts of commands are taken from these 3 locations. So a bunch of them are defaults in Go templating, which I've linked out to. They also in Helm have included all the sprig template functions. So that's where we got things like set and indent and stuff like that came from there. And then Helm does have a few custom template. At the moment, I believe they only have 2. So they had the include template that we saw before that allowed us to work around some limitations of the template function. So they have that include function. And they also have something called a required, which is fairly new, but a required function which tells, basically it tells the Helm to error out if the value doesn't exist. And we haven't started using that one yet because it's fairly new, but it's probably one we will start using for things like the GitLab URL and registration token in the runner and stuff like that, where the install just fails. So that's where you can find information on that. So jumping into one of the other files I mentioned in the templates folder. So I did say that all the files in the templates folder do get processed by the Go renderer, regardless of file extension. So that's the same in the case of this notes.txt. So we have some conditional logic in here because we haven't been using the required stuff yet, that it does this conditional logic that if you did set the GitLab URL and you did have the registration token set, we would print out, a nice message about where GitLab exists, or I've cut off a bunch of the message, so it doesn't make as much sense, but how to look at the deployment and stuff like that. Else, if there's no registration token, we print out some stuff about you missing the registration token. So interestingly enough, the thing is actually still, because we're not using those required templates, it actually does get deployed into your cluster, but you have to, this warning kind of tells you that you have to update it with this new information. And if you have the registration token but no GitLab URL, it'll also throw an error. So this notes.txt is a built-in file name that Helm will basically just print after it installs a chart. And you can put in all sorts of, any information you want to print out. So that's kind of a deep dive on building a chart, building the file structure of a chart. So after you've built one and have tested it out, you have to, in order to put it in a chart repository, you have to package it up. You have to bring in its dependencies as well. So we'll jump into packaging the chart. So the first thing to know about is the Helm repositories for charts. So a chart repository is just a HTTP server that has an index YAML file that defines what charts it has. And then it has, in that same folder, basically a list of packaged archived charts. So in order to package a chart that you have on your file system, you just run Helm package on the chart directory, and then from kind of within a folder that has these archives, these packaged charts, you run Helm repo index to build the index file. And there's additional commands you can pass to these, like the repo index has a merge command that you can just, if you already have an index file, that you can just merge the things from a new folder in and stuff like that. Another note about these Helm repositories, Helm has one added by default, which is the curated one that resides well, it's in a Google Object Storage, but the source code for it is at on GitHub in Kubernetes/charts. But then you can additionally add your own repositories, or as a user, you can add other companies' repositories to get their charts. So now we'll jump into, so previously it was about packaging the chart and hosting it just on the HTTP server. Now talking about how users actually make use of that. So users can add repositories other than the default one using Helm repo add. So this is an example of adding our own chart repository, which is hosted using GitLab pages at charts.gitlab.io. And this is the instruction we basically give people, is to do Helm repo add, call it GitLab, and point at this chart repository. And then you can do something as simple as Helm install GitLab runner. Of course, there's no default configuration for GitLab URL or the registration token, so it'll print out those messages, the warnings. So Helm itself has installed upgrade delete commands. So here's just a bunch of examples of kind of starting from the most basic to what you would normally do. So there's Helm install set command. So this is the same command as previously, except we're setting the GitLab URL, and then there's a comma, and then we're setting the registration token. So that's the bare minimum for our GitLab runner chart to actually get it to work. But better than that would be for users to actually have a config YAML file or a values YAML file that they pass. So here's an example of Helm install -f to pass a file that does the configuration for GitLab runner, and then they can version that config file. Even better often, so Helm install by default will just install into whatever namespace you currently have set with kubectl. But you can instead pass the namespace command, which I often do, and Helm will actually create the namespace for you if it doesn't exist. And in this is the third example here, I also give the release a name. So otherwise, Helm always generates a release name for, like, this is this specific release of this chart, and it just kind of generates it similar to how Docker generates container names, just kind of randomly, but you can pass the name. Then when you're making changes to your existing release, your existing charts, as a user, you have changed some config. You run the Helm upgrade command, and you have to pass it the full config. You can't just pass it changes in the config. So in this example, we're passing the config file, the same namespace as before. Instead of this command, instead of taking -- name, it takes the name of the release directly as the first argument, the chart as the second argument. And you could, instead of using file, you could use the set command, but you would have to make sure that you're setting all of the previous config plus your change config, because it'll take exactly the config and use it to regenerate a new deployment. And then finally, there's the Helm delete command, which just takes the name of the release and will attempt to spin down and then remove all of the pods and runners, and basically try to do everything but then remove everything basically but the namespace. Everything that it installed and changed but the namespace will be removed. So now just to talk about our specific Helm charts, just a little bit of information. So our Helm repository, as I mentioned, is at charts.gitlab.io. It's run using GitLab pages. The source code is available under the charts group on gitlab.com under the charts.gitlab.io repo. So it includes all the build steps for how GitLab pages builds the packages and creates the index file are in the GitLab CI YAML. Or YML. It's pretty simple at the moment. It doesn't currently maintain older versions of the charts because we've made it so simple. So basically, when you update the chart, version, you lose the previous version of the charts. So that's a limitation of our current implementation. That it only has the newest version of any chart. The charts that we currently have include GitLab. So this is just the omnibus. It has some optional, it has a bunch of, this is the chart that we kind of announced as released last month. It has quite a bit of config options to be able to use it in the most flexible way. It has the options to specify using external Redis or an external Postgres instead of the included one. It has lots of different options, I guess. I can't think of specifically something. Oh, it also has the option of specifying arbitrary GitLab RB parameters. So you can, if you want, do things like you can spin up Mattermost, you can enable the registry. It doesn't have specific config flags for that, but it does give you access to modify all of the GitLab RB commands. So it's currently kind of the most flexible, but not, and we've tried to make the basic setup user-friendly, but it's maybe not the most user-friendly, but it's currently the most flexible. We then have a chart for GitLab Runner, which is also a fully released chart. The Runner itself is simpler, so most of the changes going on in there that are coming down and are in merge requests are more about opening up more of the runner's object options that have been added in the past couple of releases, as the runner has made improvements on metrics monitoring, but also on just a bunch of more Kubernetes executor improvements. So some of those are still coming in, but the runner is very stable, and I highly recommend trying out the GitLab runner, or even using the Helm chart GitLab runner. The runner in Kubernetes is pretty awesome. Very easy way to get kind of like auto scaling runners going is if you have a Kubernetes cluster, installing it there. And then the final chart we have currently is the Kubernetes GitLab demo. So this is a chart for the sales demo. This is basically the demo that we gave at Cancun, but it's been turned into a Helm chart. And then we're iterating on bringing this demo chart up to the same standard of the GitLab chart, and eventually turning it into more of a production ready chart with a rename as well. But at the moment, this is the sales demo chart. And those are the locations in the source repository for them. We also have documentation. So in addition to the README file that each chart has within its source code, we also have docs, install docs on docs.gitlab.com. It's included in the CE and EE installation documentation. So if you go to the installation page, you have the options of like, how do you install using Omnibus? How do you do a source install? In there is also like, how do you install on Kubernetes? And it has documentation for the runner and GitLab. So that's the main source of our documentation for how to use these charts. And that's it as far as overview training. So if anyone has any questions, I'd be happy to dive more into any of this stuff. So Mark had a question that I blew by, so I don't remember the context. He says, that's awesome. I didn't know you could do that. When and where would you call this template? Which template are you referring to?
That was the one that you could override the values.
Yeah, so interestingly enough, so I wouldn't have to call the template, because in that template, there wasn't actually any defined template values. It's actually just because it's run, and now that they fixed it, these private, because the templates are now run sorted, it just allows us to, Go processes the file because it has because everything in the templates folder is processed, but it allows us to set that set command essentially allows us to, because they haven't done any sort of context protection, it allows us to rechange the values on the fly before the non-underscored files get touched. So at the point that it gets run, the values file has been processed, the metadata is there, and it's just running the render on the templates folder, but it hasn't done the non-private files yet. So it's only working on the underscore files at that point, and all of our deployments and other stuff are on non-private files. So it ensures that it will run with the upcoming fix. It ensures it'll run those commands beforehand. So it does give us kind of a way to control the values. Does anyone else have any other questions?
Nobody had any questions. I want to throw out one little sort of pro tip that I sort of discovered that wasn't obvious. If you look at all the tutorials and whatnot for creating Helm charts, they sort of start from scratch. And it's really a lot to take in when you start. But a totally different tactic is to just start from a Kubernetes object file or set of object files and just put them in the templates directory, and boom, you've got a chart. It's not, the best practices chart, but it is a functioning chart, which is just to say that a chart really is just Kubernetes objects. The values and the variable interpretation and everything else are sort of bonus syntax sugar on top. But if you just wanted to start from something like the Kubernetes demo that you already pointed out, like literally the first version of that was copy and paste and ship. Like there was no chartness to it. It was just not Kubernetes object files. So it's a good way to get started.
Yeah, for sure. The Kubernetes demo chart, like Mark said, that's the way it started out, and then so that works right away. And then then you can go back to the tutorial and see what the initial thing they were creating, and the initial thing was just getting in like making the namespacing working and like the release naming working throughout your objects. But once you have that, that's technically like you add a notes file, you add a README, and that's technically all you need to have a proper chart. You had a working chart before. Once you have that, you have a proper chart. The rest is just what you want to do. Sorry, I hit my mic. Probably sounds loud. Talking with my hands. Okay. Does anyone else have any other questions or comments?
Yeah. Kind of off topic, but how hard is it to set up Helm on a test server if one wants to play around with this?
It's so it's very easy. So if you already have a Kubernetes cluster, you mean?
No, but yeah.
So Helm is easy. Setting up Kubernetes can be easy or it can be not. We normally use GKE to spin them up very quickly, and then installing Helm to it is like literally once you run the connection commands on gcloud in the case of GKE. But if you're not using GKE and you've just booted up, what's the name of there's like
Minikube?
Minikube, yeah. So if you just got Minikube and it's more a matter of running kubectl auth login and connecting, once you've connected kubectl to Minikube and you have Helm installed, once again, it's once you've connected kubectl to your cluster and it's running as the right user, adding Helm, adding that tiller server to the cluster is just a matter of running Helm init. So cool. Once you have the Kubernetes cluster, once you have kubectl connected to it from your machine, it's just a matter of running Helm init to get Helm in. So once you have the cluster, getting Helm into it is very easy.
Yeah, awesome.
And as long as you, when you're using a Helm install, what I tend to do is, so because Helm, if you're using a proper chart that already has all of the metadata filled in with the release name and stuff like that, if you do a Helm install using the release name, the Helm delete is very, very good at cleaning that stuff up. I tend to also use, make sure I use kind of a unique namespace during an install as well, so that after I do a delete, if I want to be sure that I'm completely cleaning up any work I'm doing because I want to use the same cluster for something else or run it multiple times, I tend to also do a kubectl delete namespace to wipe out the namespace as well. But in something like GKE, combining like just the kubectl or just the Helm delete is enough for GKE to clean up the volumes as well. So get rid of the storage, clean up the different routes that it puts into its networking and all that stuff. So it cleans up pretty well at this point, which is actually a little bit easier than when you're not using Helm charts, when you've just created a bunch of services and deployments. If you don't just go and wipe out the namespace, it can be difficult to clean up everything you need to. And if you do wipe out the namespace, if it doesn't properly, if it just wipes out the volume claims without like shutting them down and waiting for the volumes to be released, then you kind of GKE sits on the volumes and doesn't know that they should go away and stuff like that.
Yeah, I currently run Docker on my server, so I know all about cleaning up.
Yeah, so Helm does make the cleanup a little nicer for sure, especially when you're testing things out.
Cool.
Does delete with -- purge delete the namespace as well, or does it still leave that lingering?
I'm not sure. Purge,
I know there were
so
times
purge
when I've had to
deletes
do purge.
the what purge does delete is so if you don't use purge when you use Helm delete, you can't reuse the same release name because it still keeps Helm keeps its own little database and config map objects of all your releases and how they were deployed and what went into them. So it even though you run a delete on a release, unless you run purge, it keeps all that information. So you can't reuse release name as a new install unless you run purge. Purge gets rid of the tiller server's information about your previous release. I don't know if, I'm not sure if it cleans up the namespace or not. I haven't tried. It might, because technically it created the namespace, but I'm not sure. Well, it might have created the namespace if you didn't have it already. Any other questions or comments? Okay, if not, that's it. Thank you, everyone, and there'll be a recording available later. Thank you very much.